Good morning, everyone. So Netan will give his second talk in his series. So over to you.
Thank you. Nice to see everyone this morning. So last lecture I gave everyone lots of exercises, so I thought I'd just start today's talk with a little homework session. So remember, I talked a lot about the idea that extensions, or I discussed at one point the idea that extensions of vector bundles / connections are related to coherent / Ram homology. Well, actually, for some of the calculations I want to discuss today, we're going to want to see this relationship in some detail. So just discuss it a bit more. So, I mean, how does this work? Well, I said that you can do this using charts and check co-cycles. So, what is a vector bundle? Remember, vector bundle V is a locally free OX module. So by definition, that's saying that it's given by the data of some open cover, and then some collection of locally free OU alpha modules. So that's the same as saying that you have some isomorphisms between the constant U alpha module and the restricted U alpha. So, for example, if U alpha is spec R, then we're locally affine, then, I mean, this is just R to the N. It's an R module, which is just isomorphic to R to the N. Okay, but I mean, the interesting data of the vector bundle, if you write it like this, is the gluing data. So we could define G alpha beta to be what we get when we take this, so restricted to U alpha instead U beta. This is an isomorphism from a constant vector bundle to V, and then back the other way. So it's actually an automorphism of the constant vector bundle, which is the same as an element of GLN of OU alpha instead U beta. So then we can actually just forget about the F alphas, and we could just think in terms of this data. So we can we think of V just in terms of an open cover, U alpha, and a collection of G alpha betas, where these are elements of GLN. Well, if you think about this isomorphism, the way we've defined it is clear that if I have three open sets, U alpha, U beta, and U gamma, which intersect, then there's got to be some kind of relation between the different G's that we get. So there's some co-cycle condition on the alpha betas. And then when are two vector bundles isomorphic? Well, that isomorphism would just amount to precomposing this F alpha with some automorphism of this. And so that gives you the equivalence relation, but I'll discuss that more in a special case, which is the one we're interested in. So similarly, I mean, we could do the same trick for connection. So I talked a lot about how you can think of a connection just locally. As the following data. So this again is an open cover. This is an element of n by n matrices with values in differentials on U alpha, and then this is an invertible matrix. U alpha intersect U beta. And well, now we're going to have a co-cycle condition, so a relation between these things, which I haven't messed up, is given by this. The check here is saying I should have checked this morning. Okay, so how does this let us describe one OX, the category of vector bundles, or X1 to RAM with OX, it's the constant connection by itself. So if we fix some open cover U alpha, then we can describe the constant vector bundle OX. Well, we could, I mean, in that case, we could just take U alpha to just be the whole of X, but that corresponds to this one. And the constant connection corresponds to this. And so that means that if we have an extension, so let's say or vector bundles, we can write E as U alpha G alpha beta, where the G alpha beta are now of the form 1, 0, 0, 1 star. And that's because we want our charts to respect the fact that we're constant here and we're constant here. So similarly, given an extension maybe let's write this as 1 H alpha beta 1. Given an extension of vector bundles with connection, we can write U lambda as U alpha 0, 0, 0 omega alpha. So we can make these lower triangular matrices with zeros in the diagonal, or 2 by 2. entry here. Oh yes, write it. Do it up here. Yeah. So that's this is a comment I get a lot when I've discussed this subject with people. Is I always write all my unipotent matrices lower triangular, which I think I get the impression for a lot of people is quite alienating. So actually, I was actually thinking about that the other day. So maybe I'm just going to have it do a little digression. But yeah, no, I mean, absolutely you can. So why I like lower triangular matrices? Well, it's to do with the fact that ultimately where we're going is we're going to want to consider, instead of just extensions of a trivial connection by a trivial connection, iterated extensions. And these will form a kind of inverse limit. Of vector bundles with connection. And the horizontal sections of these vector bundles with connection will be the things which give us the iterated Coleman integrals, which we'll want to study, which will be the functions which will define rational points. So the thing is, if you want to consider a sequence of vector bundles with connection, then you can either write it, as like, basically the problem is if you write it in upper triangular, then as you take the limit kind of, it's like, so it will, in the limit, it will be some matrix which is going off this way and this way. And if you write it in a limit, then the connection associated to E1 is disappearing off that way. So whereas if you write it as lower triangular, then it stays here, and then you kind of have E1 and then E2. So maybe it wasn't worth explaining that. That's why it's the same. Yeah, it's just the same. Yeah, transpose. Yes, you're right. Yes, yeah, yeah, that's yeah. But it is useful, and it will also actually be useful later when we talk about Galois representations, to bear in mind it's a different convention from the convention that people often follow. Okay, so maybe let's just note in this, what does this identity simplify to in this case? So in this case, this identity simplifies to the fact that omega alpha minus omega beta is equal to d f alpha beta when we restrict to u alpha intersect u beta. Yes, thank you. Absolutely. Okay, and when are two extensions equivalent? Well, so that's when we change, as I said, it's when we pre-compose this isomorphism here with some automorphism here, which in this setting just amounts to choosing some function. So in the case of vector bundles, choosing some function f alpha on u alpha, and then sending g alpha beta to alpha beta minus, say, beta plus f alpha. some f alpha in U alpha. Similarly, for extensions of connections, we have U alpha, G alpha, sorry. So sorry, this was not my G alpha beta, but rather this was my collection of H alpha betas, sorry. So now, because we've said that our G alpha beta is just given by this entry here, then we're just going to record that when we describe extensions. And so similarly here, we just record the omega alphas and the H alpha betas. And then this will be equivalent to U alpha, omega alpha plus df alpha, H alpha beta minus F beta plus F alpha. And again, should have checked the signs. Okay, well, this set modulo this equivalence relation, so I mean, it's obviously a vector space because we can add the H alpha betas. So this is exactly the computation of H1 OX by description of it in terms of check cocycles. And similarly, this is the description of H1 de Rham of X over K in terms of check cocycles. So that's the kind of explicit form of this isomorphism. So now I want to give some examples just to see how you write down elements of these groups, and for example, how you check that, say, a differential extends to an extension class of connections over the whole of X, or equivalently to a de Rham-Kolmogyi class. And I'm going to copy Jennifer's trick from yesterday evening, which is that I'm going to pretend that I'm saying something actually about modular curves by just doing this for the example of X on 37. So remember, this was y squared equals minus x to the 6 minus 9x to the 4 minus 11 squared plus 37. So actually, in general, for a vector bundle, it's a little bit difficult to say what chance you might need to take, but for these extensions of vector bundles by a theorem of Serre, we can take any cover of X by affine opens, and we can always describe our class in terms of those charts. So in this case, we could take this curve has a natural cover in terms of two affine varieties, so we could take spec of R0, where 0 is Q of XY, there's f of X. Y squared minus f of X. And take this one at infinity. Where u of u is 37u to the 6 minus 11u to the 4 minus 9u squared minus 1. And then we can glue these via an isomorphism of R1 1 over X, R infinity 1 over U, which sends X to 1 over U and Y to V over U cubed. So that's the standard way of describing a hyperelliptic curve as a scheme. Okay, so what do we want to get a non-trivial element of H1XOX, then we're exactly just asking for an element of this ring, which doesn't come from R0 or from R infinity. So this will be spanned by y over x and y over x squared. And that's because once you go to y over x cubed, then you've this relation, or its inverse, sorry, means that the class is trivial. Okay, well, I'm going to stay with x naught 37 for a little bit and come back to this thing I mentioned about residues and extending connections, or equivalently extending cohomology classes to cohomology classes on an open set to the whole space. Recall. So we asked this question of extending omega, sorry. To an extension of connections, or equivalently a Durand cohomology class. Is related to the residues of omega at the points. So let's say now that x is a curve, or in general. So in particular, if x is a curve, then this is just a set of points. And we're taking the residues at those points. So this question is actually the Durand analog of this question, which was discussed yesterday about when does a group cohomology class actually come from a cohomology class in a modular curve, or a parabolic cohomology class, and that's related to some restriction to a stabilizer, which is related to this residue. So this is like the kind of algebraic Durand version of that. So why is the residue related? So remember, the residue was the a-1 coefficient of the expansion of omega at x. And so, I mean, the point is basically just about integration on a of t. So let's say that we've got some x in x minus u alpha a bar, and t is a parameter at x. So yeah, let's say we could write omega as some a n p to the n dt. And I claim that extending omega to x is the same as being able to formally integrate omega. So and well, I mean, you can check you can formally integrate this power series if and only if the a-1 term vanishes. But maybe I can just say a little bit more about why is this the same. Well, I guess, I mean, we'd like to say that we choose some open u beta, which contains x. And then, so for example, suppose that this, let's say, formally integrate omega, let's say that f is of omega. And suppose we could put f was a function on ub, then we'd have that df minus omega was equal to 0. So this would actually satisfy this co-cycle condition. Now, of course, we can't usually do that because f is going to be a transcendental function. But actually, all we want is we just want some f in u beta intersect u alpha. So sorry, f in a function on that such that df minus omega has no poles at x. So if we shrink u beta, we can just write like this. So actually, we don't need to integrate the whole of omega. We can just integrate, so the kind of what's the principal part, I think is the term in Riemann surface theory. So the sum of the n less than 0 so then by construction, the f minus omega has no pole. And because, I mean, t was a parameter, so in particular, t is an algebraic function, and this is just a polynomial in t. So this is actually an element of, well, again, maybe if we shrink u beta a bit, u alpha intersect u beta. So let's do this again for x naught of 37 and see what we get. So let's take a differential of the form omega I equals x to the I gx of y. So then how do we, and then we want to see if we can extend this to infinity. So in this case, there are 2 points at infinity, and if you think about it, they're defined over qi. So we'll just pick one of them. So now I'll call that one infinity. Maybe I'll call that one infinity plus. So in terms of uv, that's the point. uv equals 0i, let's say. So in this case, u will be a parameter at infinity plus, and v inverse is going to look like I times 1 minus 9 over 2u squared, 199. We'll actually need this one. U to the 4 plus order u to the 6. Yeah, just that. Okay, so this allows us to compute the residues of omega I. So what does omega I look like in terms of uv? Well, omega I will be equal to minus u to the 1 minus I, u over v. So, well, maybe is not a surprise if you've seen a basis of canonical differentials on a hyperelliptic curve before, you'll see that omega 0 and omega 1 extend because they're actually global sections of x, of sheaf of differentials on x. Omega to the omega 2 has a pole. The residue of omega 2 is going to be equal to minus I think, and residue of omega 3 is going to be equal to 0. residue of omega 4 is going to be equal to minus 9i over 2. Sorry, actually, no, plus 9i. So where does this come from? I mean, this is just from multiplying this by du and u to the 1 minus I. So for example, how do we extend omega 3 to to infinity? I think if I've done my calculations correctly, I think we can take omega 3 minus a half du over v. So that's actually element of omega of, what's it calling, u infinity. And then you can do something similar for the other, well, so you can't do it for these ones, but you can do it for this plus 9 over 2 this. So for example, in this case, we see a basis of h1 gram of xk given by 0 omega 1, 9 omega 2 plus 2 omega 4 and omega 3. And these two will restrict to a basis of h1x ox, which corresponds, what I was saying yesterday, to the fact that this is a basis of the F1 part of the Hodge filtration under M. Okay. So that, hopefully I convince you that that's not so complicated. And in fact, the general theory which comes up in non-abelian Chabauty is not really kind of theory of connections, Hodge filtrations, and iterated integrals. Is not much more complicated than that. The only difference is, for example, for non-abelian Chabauty in depth 2, including quadratic Chabauty, you just replace something like this with something like this. So this introduces the notion of unipotent connections. Yes. Oh, I mean, just that you can, I mean, that you can calculate these things. I mean, it's. Yes. So I mean, so for example, in the language of, so I was explaining it in terms of connections, but in the language of, sorry, in terms of Durand cohomology, but in the language of connections, this is saying that so I can define this connection, omega 2, as a connection on what I was calling U0. And I'm saying that it doesn't extend to the whole of X, or it extends to a connection with logarithmic singularities. Yes, exactly. But if I added 2 over 9 times omega 4, then it would extend. And so now, I mean, when we look at these kinds of things, we'll see some kind of similar but slightly more complicated conditions. Yeah. Yeah, so they're at the point infinity plus. So technically speaking, there are 2 points, but they're Galois conjugates. So, yeah. And in fact, so I mean, the reason that I took this function to remove the residue was because this will be the one which also removes the residue of the other one. And that's to do with the fact that this is odd with respect to the hyperelliptic involution, or if I can just say odd with respect to the Atkin-Lehner involution, pretend I'm doing something about modular curves. And so we want to take a function which is odd with respect to the Atkin-Lehner involution. Okay. So this is a construction. So suppose we're given some omega 1 up to omega n. And then we're going to define a connection nabla on v equals ox to the n plus 1 by I guess d minus lambda, where lambda is equal to this lower triangular matrix omega 1 up to omega n. And I'm going to suppose that this is flat, which for our purposes, we can just say that X is one dimension. And then I'm going to define the iterated integral of omega n up to omega 1 in terms of horizontal sections of this connection. So I'm going to do this first in formal categories. So suppose we're given some x and x of k. Going to define a function which I call omega n up to omega 1 x, which will be an element in the formal completion of the local ring at x. So again, in the notation from just there, we could just think of this as k double brackets t. What am I going to define it to be? It will be so I mean, a section of this vector bundle. So the trivial vector bundle is just an n plus 1 tuple of formal functions. I'm going to take the n plus 1th coefficient of the horizontal section S, which is a section completion at X. It's a formal section, the horizontal section which satisfies its value at X. It is 1 in the first coordinate, 0 everywhere else. Okay. I'll say in a second why this is a good definition. And if now k is equal to c, and we have a path in X, then I'm going to find the iterated integral of omega n up to omega 1 along that path to be, there's a complex number, n plus 1th coefficient of parallel transport isomorphism of 1, 0, 0. So parallel transport, remember, is going from this thing here is an element of the fiber at gamma 0 of V, and this thing here, an element of fiber at gamma 1. So what do these objects look like? So I'm just maybe to familiarize yourself with them, it's worth checking two properties which are often how iterated integrals are defined. So one is that if you take the differential of this function, it's equal to taking the function you get by throwing away the last differential, and then multiplying that function by the differential omega n. And so that doesn't quite uniquely determine this function because it doesn't determine it up to a constant, only determines it up to a constant, but then we also impose that its value at x is equal to 0. So that actually uniquely determines this power series. And then another exercise for the complex paths, which is just kind of essentially boils down to multiplying unipotent matrices, is if I have two paths, gamma 1 and gamma 2, and I compose them, then the iterated integral I get is a sum of products of the first path oh, sorry, what am I doing? Plus ones. And the second part. Well, I mean, my convention is that if the integral of an empty set of differentials is just 1. So it just means, I mean, this is a this vector bundle is OX to the n plus 1. So a section is just given by something. So this one is the n plus 1. So this is the one with an x is a function. The one with a path is a number. And I guess the relationship between these two is that this function, if you think of it complex analytically, will converge in some neighborhood. And if you take a contractible neighborhood and take a path on that contractible neighborhood, then this number will be the same as evaluating this function. And I suppose the goal of this theory of iterated Coleman integrals is to be able to do this definition now in the rigid analytic category. And the definition kind of involves elements of both sides, but it's maybe it's also just kind of fundamentally rather different. However, before I get there, I will get later today onto the rigid analytic category. But before I do that, I just want to keep banging on a bit more about this business of how do you extend a connection. So, and the reason I want to discuss this problem is I think this gives you actually quite an indicative flavor of how the theory, say on the local side and also on the computational side, changes from the abelian to the non-abelian setting. So let's suppose that we have some nice curve x, and we have an open y. Yeah. Yes. So hopefully my convention is the most common one. There might be some people who have a different convention, but there is an identity that you can check about what happens when you do this so-called shuffle product identities. So for example, you can check that omega 1 omega 2 plus omega 2 omega 1 is equal to omega 1 times omega 2. Yes, so no, so absolutely you're right. So this integral is very different from taking the n form that you get from wedge. Because I mean, we're mostly interested in the case of a one-dimensional thing. Yeah. So it's yeah. So it's not. There's no simple relationship between the two. So there are complicated relationships, but that's kind of another story. So let's say we've got some nice curve in an open Y, and I want to ask two questions. So the first question is, so let's say we're given omega 1, omega 2 in here. When does the connection d minus lambda, where lambda equals 0, 0, 0, omega 1, omega 2, 0, 0, 0. So this is a connection on OY3. Extend to X. And if you recall, even in the example of this, there's a abelian setting where we just looked at this one here. When we were able to extend the vector bundle with connection to 1 on the whole of X, the vector bundle we got was no longer the trivial vector bundle. We got a non-trivial vector bundle, a non-trivial extension class. And so when we say extend it, we're also asking about the existence of a vector bundle. And then another question you could ask is, when does there exist an eta in omega y such that eta extends? So this question actually, this is a little hint from the answer to see the answer that we're going to get for those of you who are familiar maybe with group cohomology. So maybe I'll make this remark over here actually. So this is a remark for group cohomology enthusiasts, which I know there are some in the audience. So I mentioned, well, I mean, I didn't quite mention, but I was minutes away from mentioning this Riemann-Hilbert correspondence, which is an equivalence of categories, flat connections, well, at least if X is projective. So in particular, in this case, on X over C, and representations of I1 of XC, some base point. So you could plug in this equivalence of categories into this question, and then this becomes a question about representations of the fundamental group. And then the question it becomes is, suppose you have two characters, i.e. abelian representations, row 1, row 2 are reps from I1x of C to lower triangular matrices. So let's just say that maybe I'll actually just write row 1 as 1, row I as CI 1. Then when do row 1 and row 2 extend? So when can you form some iterated extension to 1, C1, C2, 1, 0 star for some star? So this C1 will actually be, well, so it's a homomorphism from the fundamental group to, so I guess these are complex reps, so to the complex numbers. And this star will in general not be homomorphism, satisfy a more complicated identity. Okay, but let's do the Durand version. Extend to so exists a rect row into here, yeah, this form. So equivalently, you could say, when does there exist a cochain epsilon I1 of x complex numbers such that this thing is a homomorphism. Does that make sense? C2. Yes, yeah, they are. Yeah. So that's what I mean by extending the. So this thing, if you think about it, it's an extension of the trivial representation by row 2, and it's also an extension of row 1 by the trivial representation. So it's sometimes called a mixed extension. This is just I guess an extension of local systems. So it's this is just on the representation side. This thing here. So no, this is an extension of representations, I guess you could say. But then under the Riemann-Hilbert correspondence, it gives you a vector bundle of flat connection, which is this one we're talking about here. Okay. So being able to extend, so suppose there exists an extension of lambda. We'll now go back to the Durand question. To let's say it's U alpha lambda alpha beta. Maybe I'm going to call them F alpha betas. So what does that mean in particular? It means that every time we take an x in x minus y a bar, we have some connection, let's say lambda x, which is an n by n matrix on some open neighborhood of some neighborhood. And how's it going to be related to our original lambda? Well, we plug in what we were discussing earlier. The relation is going to be that this we have. So we can write it as f I call it lambda x is equal to lambda f df. But now we do the very simple thing, which is, as I think I mentioned yesterday, is basically the equation which is at the heart of kind of classifying vector bundles with connection, is that we just noticed that this actually tells us what lambda x is in terms of f. Okay, so now we translate, and remember the condition is that we've started with this matrix of differential forms which has poles at x, and we want to, our game is now that we want to find this unipotent f such that when we apply this slightly bizarre looking operation the first time you see it, we actually end up with something which has no poles at x. So f is of the form, for this to be a unipotent connection on the whole of x, we need f to be of this form. where these are some functions which are now allowed to have poles at x. And then we can actually just write out what lambda x is. If I didn't mess it up, it's this. Here we have, we get the familiar formulas on this entry and this entry because these are actually, this is a quotient connection and this is a subconnection. 0, 0, 0. And then we get some funny looking thing here. So this is, sorry, this thing here is the bottom left entry. So this is a little bit more complicated than what happened in the abelian setting. And yet somehow, like, I would say basically all the progress that's recently been made on like quadratic Chabauty is really complications of this order of magnitude. It's just like, you know, it's like, I guess is often the case, you know, you go from being able to do something with a 2 by 2 matrix to a 3 by 3 matrix, and suddenly the things open up a lot. So this maybe seems a bit complicated, but in some sense, the reason I'm telling you this is because I want to convince you this is actually almost as complicated as it gets. So what conditions do we get? So, I mean, the thing we want to be able to extend this connection is we want to be able to f such that lambda x has no pole. So, well, I mean, as we've already discussed, this implies that we'll need the residue of omega 1 to be equal to 0 and the residue of omega 2 to be equal to 0. And actually, if this holds, then we can end up without loss of generality. We can choose one f2 such that the fi is congruent to omega I modulo t to the n, so where t is a parameter as usual at x, and n is just the order of pole of omega 1 plus the order of pole of omega 2. And then it turns out this formula then, basically this term here cancels out, and so then we can find F3 if and only if the residue at X of this new thing, omega 1 times F2, is equal to 0. So that actually answers the question of when this vector bundle with connection extends. And then for the second question, when can we find eta as above, so as in question 2. So it turns out that the flexibility of being able to add in an eta means that we no longer have to impose this condition that the residue vanishes, because we can choose eta so that it has the appropriate residue at that point. Except we're not completely free to choose the residue of eta, because if you have a 1 form on y, then the sum over all points of x of its residue will be equal to 0. And so it turns out that this is if and only if the sum over all x and x of k of the residue of x of, well, strictly speaking, I should call this f2 of x because it depended on x, is equal to 0. But this quantity actually has a meaning. This is by Serre duality. Turns out you can show that this is a very nice way of defining the cut product in the Ram cohomology on a curve. So this is, I'm going to say almost by definition, the cut product of omega 1 with omega 2 in H2 to Ram. So if I now go back to this topological remark, what this is telling us is that we can extend, if we've got two de Rham cohomology classes, we can construct this iterated extension if and only if their cut products in de Rham cohomology vanishes. And the topological analog of this is that if you have two homomorphisms of a group, then you can extend the two kind of 2x2 unipotent representations they define to a 3x3 representation like this, if and only if the cut product in group cohomology vanishes. So the Riemann-Hilbert correspondence kind of already told us the answer we should expect. So now for the remaining time today, I want to now get into some rigid geometry. So get a bit more p-adic. P-adic version. And we've already seen lots of hints of what the kind of appropriate p-adic version of this theory I've been discussing should be in Samuel and Jennifer's lectures. So the kind of blessing and the curse of doing p-adic analytic geometry is that you have a kind of very large range of choices of what category you work in. And this is, as I'll explain later, is a kind of a feature because it means that you have lots of interesting extra structures because you can look at things in different ways. But of course, it is a bit of a bug when you're first learning the subject because there's a million billion different definitions and how they're related and so on. So I'll try and keep things fairly concrete. So, I mean, maybe I should say we're ultimately going to be interested in the context of where we have some variety of a ZP, so a smooth model of some, say, curve we're interested in over QP. On some variety, let's say. X over QP with good reduction. That means that we can form some X over ZP. And the first kind of way we can analytify that is that we can take the formal completion of this along the special fiber, and that defines what's called a p-adic formal scheme. So take that definition. P-adic formal scheme. The morphism formal schemes. I call it. So the convention and the people who invented the subject is that they often call a p-adic formal scheme P, which has its disadvantages, maybe when you're trying to. So if you're never sure, if you're ever not sure if it's a big P or a little p, you should definitely ask me. So it's just a formal scheme where P is tending to 0, basically. So that's a very general object, but we're mostly going to be interested. We're mostly interested in, actually just only interested in p-adic formal schemes which are flat and finite type. So that means that locally we can just think of them as spiff of R. So really we can even forget about the spiffs, and locally we just think of R is some topological algebra. So it's like R, for example, is where in the topology e to the n tends to 0. And really, we're actually even going to be interested in an even more special case than this. Is we're going to be interested in the case where we start with variety, like the curly x we had here, but I'll just call it normal x over zp. And then we can take its completion along the special fiber. So take P equals completion along special fiber. This is a p-adic formal scheme. So let's give an example. That's really the only p-adic formal scheme we're going to care about. So a nice example is, e.g., we could take x to be just a1 over zp. So just spec of zp of x. And then the formal completion is the brackets, angle brackets of x, an x to the n, zp double brackets x, such that an tends to 0. And more generally, you can define so our finite type is saying that we're going to locally look like d of x1 up to xn, modular f1 to fn. So by construction, just from the fact that it's a p-adic formal scheme, we always have a special fiber. Just fiber product formal schemes. And then a nice thing about p-adic formal schemes, which will relate it to the theory that has come up in some of the other talks, is that it also has a generic fiber. And this generic fiber will be a rigid analytic space. And so locally, we take our complete ZP algebra R, and we just tensor it. Not completed tensor, just normal tensor with QP. So e.g., ZP of x goes to, so if you think about it, when you tensor this with QP, you just get the usual Tate algebra. And so that says in formal scheme language that if I take A1 ZP and then I formally complete that along the special fiber, and then I take this generic fiber. So this generic fiber is written as P subscript QP. And this is just equal to the usual closed ball of radius 1. So now a warning. Which is also a chance to draw some pictures, which one should always do in this subject, is that there are two, if you say we start with so our smooth variety X over ZP, then there are two ways to construct a rigid analytic space out of this. So the first is, which is maybe the more familiar one, is you could just take the generic fiber, just in the category of schemes, and then you can take the analytification of that as is defined in any book on rigid analytic spaces. And then a nice feature of that is that every QP point of X is going to give you a point, QP point of the analytification, and also over extensions. And then the other thing you could do is the one we've just described. You could take this formal completion, and then you could take this generic fiber, sometimes called the Berthelot generic fiber. And these are actually very different rigid analytic spaces. So this is going to be an affinoid open subset of this one, in the case, say, when you start with something affine. So let's just do this for A1. This thing, as I said, is the closed ball of radius 1. And then, well, this thing is the analytification of A1, which, so in particular, is QP points is the whole of A1. So this is some closed ball inside A1 QP. But this object will be better for us, and that's because by restricting to this smaller space, we have. If you look at this example, you'll notice that every point of the closed ball of radius 1, in an obvious way, we can reduce it to a point on A1 of FP, but we can't do that here. And that's something that will be very useful, being able to reduce points. The P of QP as a specialization map. This is just a map of sets. Right, so this thing here is a set just coming from taking the Zariski topological space P. And then this thing here is the set, or locally it's a set of maximal ideals, some affinoid algebra. And so how can this be defined? So we can define it locally by the actual, so the special fiber actually has a specialization map, which is actually a map of formal schemes. Thinking of a scheme as a formal scheme. just being like a constant formal scheme. And then using the fact that for finite extensions of QP, so maps so the points of let's say k points of PQP onto OK points of P. Or locally, if we say we're given by spoof of R, that corresponds to all the homomorphisms from R tensor QP to K actually descend to homomorphisms from R to OK. Okay, then the next thing I need to define, which has actually already come up several times in the context of studying a residue disk of a point, is a kind of generalization of a residue disk called a tube. So I think this is actually sometimes maybe, I mean, at least I found a slightly off-putting feature of the theory is not only is there a lot of terminology, but some of the names are slightly unusual, like tube, wide open, so on. So what's the tube? So suppose we have our formal scheme P, and suppose we have some subvariety Z inside the special fiber, then we're going to define something which a priori is just a set, and then we'll kind of see how to think of it really in terms of algebra and geometry. The pre-image of Z. This subvariety, I'm not imposing that it's closed or that it's open, but I want it to be an intersection of an open with a closed. So locally, let's say that Z is equal to, let's say we have F1 up to Fm in O of P. So this is local on P, so we might have to shrink P a bit. And G1 to Gn in O of P, such that Z is equal to the zero set of the reductions of Fm intersected with the union of the opens where these functions don't vanish, mod P, P of G1, P of Gn. So maybe this is one case where I should keep going over here. So then, what's the tube of Z? It's just going to be equal to the set of points Z, P of QP. So it's a preimage of so it's some subspace of a rigid analytic space, and actually has the structure itself of a rigid analytic subspace. To see that, we'll define it in a more rigid analytic way. So the analog of asking that the FIs vanish is asking that their lifts have absolute value less than 1. And the analog of being in the union of these places where the GIs don't vanish is asking there exists some J such that the J of Z is equal to 1. So these, so these are, yeah. Oh, but here, yes, sorry, yeah. Thanks. Thank you. So let's just do a simple example. We could take well, any variety PFP. We could just take Z to be a point. then X is equal to what we were previously calling the residue disk of X. So it's going to be, as a rigid analytic space, it's going to be isomorphic to the open ball of radius 1, which we're going to call B01 minus, so it's ball of radius 1. To the D, where D is the dimension of. And remember, this open ball, this is a space defined by an algebra. Now here, the algebra here is it's the set of functions such that they're all eta less than 1, ai e to the I tends to 0. Okay, is there any questions or ambiguities about my definitions? Maybe I can just give an example, which came up yesterday in Jennifer's lecture. About why, say, in Coleman integration or in Chabauty-Coleman, you're interested in this language of tubes. So remember, yesterday in the lecture, we had a hyperelliptic curve. And then we had some open, which was X minus Weierstrass points. Then, and so maybe, so this was X over QP. And then we had some smooth models of these X and Y, the ZP. Then actually, when we were computing Coleman integrals, we had this thing where we chose a lift of Frobenius, but it didn't converge on Weierstrass disks. So we actually had to work with computing Coleman integrals. Like Kedlaya. We don't work on what we might think, which is the analytification of X over QP, but on the tube of special fiber of Y. And in fact, as will come up later, we worked not on this space, but a slightly larger space, which was this issue of overconvergence. So that's one example, but another maybe seems like a slightly similar, sillier example was in Samuel and Jennifer's lectures. We've often wanted to study integrals or differential forms when we pull them back to a residue disk. And so that means sometimes even if we start by working with the usual analytification, we actually will restrict to the tube now of a closed subvariety. And this language of rigid geometry and rigid analytic connections that was developed by Berthelot kind of, I think, clarifies a lot of these features. So the idea now is that we want to study analytic connections on, say, X of FP. So we start with some X over FP, say, and then we want to maybe find some formal scheme, some lift of it, and construct connections on that. And so I suppose we want a kind of nice, well-behaved theory. Which looks similar to theory of flat connections on varieties over QP. So it seems like, we're in good shape because, we have a notion of functions and we have a notion of differential forms in rigid geometry. But I guess actually even this example here, so we take x equals a1 and xqp, remember, is qp of x. And then we have this notion of omega f of xqp of qp, which we can just think of as qp of x times dx. And then we have a differential map from here to here. And well, I guess just like in the case of curves algebraically, if we were to study just naively analytic connections on the tube of XFP, so analytic connections on here, just by naively copying and pasting all our definitions that we had before, then we'd get the property that omega f x qp over qp modulo d of qp of x is infinite dimensional. So in the language of extensions of connections, that would tell us that we have infinitely many non-isomorphic extensions of connections. So this is like a kind of meant to be an analog of our de Rham-Cohen-Morgy group. And if you remember, say, for example, in Jennifer's lectures, compute Coleman integrals, we took a basis of de Rham-Cohen-Morgy, and we don't want to have to make that basis be infinite because then we'd be there all day. So this definition is wrong. And the solution as kind of came up in Jennifer's lecture yesterday is this notion of overconvergence. So maybe I'll talk about that tomorrow.
Are there any questions or comments?
Formal completion. Yes, thanks. Yeah. Yeah, sorry. Oh, sorry. Yeah, X hat is the formal completion along the special fiber. So it's this one. Is that? Yeah.
Any other questions? Just one from me, quick one. So this description that you gave, the reinterpretation of H1 in terms of these vector bundles. So if you take, if your X is let's say an abelian variety, so H1 has this, it classifies all the extensions of the abelian variety via say GA. I mean, do you see any way to kind of relate to these two things? Like the de Rham cohomology also has that that these are extensions of the abelian variety.
So
GA has some split. Yeah.
Yeah. So I think there is actually a very nice dictionary which relates the universal vectorial extension on an abelian variety to, well, something which can be described in terms of the RAM fundamental groups, but I guess it's really more like frame bundle on the kind of universal extension of OA by itself in the category of connections. So these things are both going to be GA to the G choices. And I think that they're actually the same. And there's, I mean, you can say more things in that direction. You can actually also describe this in a kind of Tanakian language. And so I believe actually that there's a PhD student of Thiago Fonseca in Brazil who's working on this. So he might be the best person.
Yeah.
So I guess I would say that the analog of that is that we've quotiented out by D. So you have infinitely many overconvergent modular forms, but I think some of them are exact. I did want to mention this modular forms in the context of this overconvergence issue and this infinite dimensionality. So when we're going to define these categories of connections, which will be called isocrystals, we're going to say that we just want to look at overconvergent isocrystals, and that gets a nice kind of finite dimensional theory. But actually, it's very interesting to also study what you get if you don't impose this overconvergence condition, which is called convergent isocrystals. And so overconvergent isocrystals are a subcategory, and one of the things that's interesting about them is that they're not even actually a full subcategory. So you can restrict an overconvergent isocrystal, just think of it as a convergent one, and you get new morphisms. And so in the context of modular forms, this comes up when you take the unit-root splitting of the Gauss-Manning connection on the universal elliptic curve. And so it's wrong to say that, it's too judgmental to say that this convergent isocrystals, ones which don't overconverge, are bad. They're just different, and we should try and understand them as well.
Okay. If there are no more remarks, let's thank our speaker again.